Hello, this is Jack Jackson. In this video, we're going to be talking a little bit about the derivative of an inverse function. So if we start with the function, say, for example, natural logarithm of x, which I can type here into this GeoGebra application that I wrote, we can type in the formula there, ln of x, and it will be graphed here if we have this checked. Then we type in its inverse function, e to the x, and it's graphed here. Now, if these are truly are inverse functions of each other, you'll only see one blue graph in this application here. If I were to type in something different here, like this, you'll see two different graphs, because one of these is actually the inverse function of this, e to the x, and the other one is not. So let's go back to to this. So if you see one there, you probably got the formulas in there correctly that are inverse functions. Now, what is the relationship between these two things? Well, the inverse relationship is that we're just switching x and y. We're switching all the ordered pairs. So, for example, this has the ordered pair 1.5, comma 0.41, at least approximately, and this one has the ordered pair 0.41, comma 1.5. They're exactly backwards from x and y. And what that means graphically is that they're reflections over this line y equals x. So that means that if you connect up the pre-image and image points, so think of one of these as the pre-image, then the other one is the reflected image of that, then the line segment connecting them is perpendicularly bisected by this reflection line y equals x. That's just a general relationship between two inverse relations. Now, they don't necessarily have to be functions for that to happen, but if right now we want to restrict ourselves to situations where we actually have functions for both of them, which by necessity means that they're one-to-one functions. So the question is, how does the derivative of this ln of x, what is it? How do we find it? And what does it have to do with the derivative over here of e to the x? Now, at this point, I'm going to assume that we know that the derivative of e to the x is e to the x. But at this point, maybe we don't know the derivative of the natural logarithm of x. So what do we do here? Well, remember that the derivative is just the slope of the tangent line. So let's look at the tangent lines here. And here you can see both of the tangent lines. And, of course, the slopes of those lines, being the derivative, is how much they go up or down when you go right one, how much the tangent line goes up or down. So the derivative of this blue logarithm function at this particular point for a is the length of this vertical vector here, or a positive 0.6, well, 0.6 repeating, 2/3. And then the derivative over here on this one is the length of this vector here, which is 1.5, or 3/2. This is 3/2, this is 2/3. Do you see the relationship? They're actually reciprocals of each other. Anytime you reflect a line over that axis, you get reciprocals for the slopes. So let's just see if you can see that. If this is y equals mx plus b, then this is x equals my plus b, right? Just switch the x and y. Solving this for y is 1 over m x plus b over m. So the slopes here are reciprocals of each other when they reflect over this line. And that's exactly what's happening here. When you're reflecting the graphs over that line, y equals x, you're also reflecting the graphs of the tangent lines. Now we can kind of see this if we move this point A around, and no matter where we are, we're going to get this relationship that the tangent lines are going to be reflected over that line as well, which you can kind of see there. So notice as the The slopes get smaller and smaller on the logarithm as we go out to the right, and the slopes get larger and larger on the exponential. Okay, and they're exactly the same when x equals 1. They're both the same. They're both 1. Like they're parallel at that point. Otherwise, they're going to cross each other on that line, y equals x. Okay, so can you see that? So what we found is that if we know the slope of this curve at this reflected point, its reciprocal is the slope over here for the curve that we're looking for. Now remember, what we're looking for is the slope of this blue curve, the inverse function of the one we know. So we know the derivative of e to the x is e to the x. But what's the derivative of the log of x? Well, it's going to be the reciprocal of the derivative of e to the x, but not evaluated over here at a, at this point here, which is what? Well, it's x here is the y here, so it's evaluated at f inverse of a. So here's how you would write that down. The derivative of f inverse, remember f inverse is the blue one, the g, the ln of x in our case. It is, the derivative of that function is 1 over the derivative of the original green function, okay, but evaluated at f inverse of x. And here's what that would be for this particular one. So for this, well, let's do the proof first. Let's do the proof here. So here's the formal proof. You let y be f inverse of x. That means f of y equals x. Now we're assuming these are one-to-one functions, so both f inverse and f are functions, so this makes sense. So remember that the f is the green one here, so the output of the input here is the output over here on the original one, on the f inverse. Right, so what's the output y here is the input here. Now we take the derivative of both sides with respect to x. Well, the derivative of x with respect to x is 1. The derivative of f of y with respect to x is just f prime at y, but the y and the x have not the same letters like we did a substitution. We use a substitution rule, or in other words, the chain rule, which says we must multiply by the derivative of the y. Now solving that for dy over dx, which is what we're actually looking for, the derivative over here on the blue graph, we just divide by f prime of y. So the derivative of y with respect to x is f prime, the derivative over here, but evaluated at y and then reciprocal that. But y, of course, is f inverse of x. So there's the proof, and if we apply that in our particular case, the derivative of e to the u is e to the u. So it's 1 over e to the u, where u is whatever this f inverse is, ln of x. So it's 1 over e to the power ln of x. Well, e to the power ln of x is just x. So this graph right here is the derivative of the blue graph. Okay? And it is just 1 over x. You can see that, for example, here at some of the points. Let's put in some things and see if this works out. So, of course, if you put in 1, you get 1 for the derivative. If you put in 2, we should get a half for the derivative, 0.5. If we put in 3, we should get a third. That's 0.3 repeated. Yeah, it's rounded off there. Put in 4, we should get 0.25. Put in 5, we should get 1/5, which is 0.2. Look over there, see it's working out. So this is 1 over x. However, you have to be a little careful here. 1 over x is defined for all real numbers except for 0. But ln of x is only defined for positive numbers. So we would really need to put a restriction on this. G prime of x is 1 over x, which is what that reduces to, provided that x is positive. and then you would only get this first quadrant graph for the derivative. Notice that what we normally know about derivatives, the original function is increasing, so the derivative is decreasing. We have a vertical asymptote right here on the y-axis as x approaches 0 from the right side. The function is approaching negative infinity, and its slope of the tangent line is getting bigger and bigger and bigger as we go that way. See, those slopes are getting bigger and bigger, approaching infinity. And so that means the derivative is going to have a vertical asymptote going up this way, approaching infinity. As we go further and further out to the right, those derivatives are getting smaller and smaller. That tangent line is getting closer and closer to horizontal. Never gets horizontal, but it's getting closer and closer to that. So the derivative has a horizontal asymptote out to the right of zy equals 0, the x-axis. So it has the correct features that we would expect. And let's just check one more point here. What if we put in 0.5? That's 1/2. We should get 2 for the slope. And we do there. And so we can see how that's going to work out for us. So with this GeoGebra app, you can put in any function you want here that you want to find the derivative of. Put in something here where that's the inverse function where you know the derivative of it, and then you can use this to investigate that situation. So let's apply this rule where we already know the derivative of a function a different way. So for example, let's look at this one right here. If f of x is x to the third, then f inverse of x is x to the 1/3, or the cube root of x. According to the rule that we just derived, the derivative of f inverse, the derivative of x to the 1/3, is 1 over f prime evaluated at f inverse. In other words, f of x is u to the third, x to the third. So think of that as a substitution. U to the third, do the derivative with respect to u, but then evaluate the whole thing at u equals the cube root of x, or x to the 1/3. Well, the derivative of u to the third is 3u squared. Now put in the cube root of x. This is x, well, you can write it this way, 1 over 3 times the cube root of x squared. We also could rewrite that as a power function. Okay? Now, in this case, it would have been a lot easier just to do the power rule over here on the inverse function, but we're going to show that you're going to get the same result that you did here. So it's just an illustration that this works. So the derivative of f inverse is a lot easier to do directly using the power rule. It's 1/3 x to the negative 2/3. In fraction form, this is 1 in the numerator, 3 is in the denominator. This is x to the 2/3 in the denominator. 2/3 power is 2 for the power 3 for the root. So that right there is exactly the same thing that we got here. So you can see that this does work for this particular example. But what really makes this work well is the fact that it works for things that we can't do directly a different way, like the logarithm function that we just looked at, or inverse trig functions. So let's look at one more, or let's look at this same one here with the application. So this was, let's turn off some of this stuff. And let's look at this. This was, okay, so the one we were looking at is x to the power 1/3. Okay, which is this one. That's still a reflection of the e to the x. And its reflection should be x cubed. Now we should be down to just one blue graph now. Okay. Not sure what that is. that is the derivative of x cubed, and I'm not sure exactly why that's there, so we're gonna hide that if we can here. Okay, I've got this cleaned up now. So this is f of x is this green one here, which is x cubed. F inverse that we want to try to find the derivative of is the cube root of x, or x to the 1/3. When we look at the tangent lines, once again we have that same relationship that we reflect. Well, first of all, before we look at that, look at the reflection again. There's the reflection over the line y equals x. You can see that. And if we look at the tangent lines, again, we see that they're reflections. And we can see that these are reciprocals of each other, at least approximately. That's approximately a fourth. That's approximately 4. And we can experiment a little bit with this to see some different values there. Okay, but we still get this same result, that these tangent lines are reflections of each other over that line. And so we still see the inverse function rule work. So the derivative, if we were to let's get rid of that, the derivative of that function then is this function here, okay, which we saw that as 1/3 x to the negative 2/3. The derivative of the original, the f of x, its derivative is 3x squared, which is here. And notice that these two are not exactly reciprocals of each other, but they're reciprocals evaluated at the reflected point, if that makes sense. So when we look at a reflected point here, you take the derivative at this point on one, it's the derivative of the other one at this point. Those two derivatives are reciprocals. Okay, so anyway, that illustrates the what's going on there with the inverse function rule. And of course, the benefit of the inverse function rule is that we can use it to find derivatives of logarithm function, which we just did, and also for inverse trig functions and any other function where we know the derivative of the inverse of the function that we're trying to find the derivative of.